Today, artificial intelligence is a multi-trillion-dollar industry. It feels inevitable. A force of nature. A technological revolution that is changing everything about our world, from medicine and finance to art and war. But this entire revolution almost didn't happen. In 1986, AI was not the future. It was a joke. It was a dead field, a scientific embarrassment, a burnt-out crater of broken promises and wasted money. Billions of dollars, adjusted for inflation, had been poured down the drain. The most advanced research labs in the world were quietly laying off their AI teams. The media, which once promised robotic maids and thinking computers, now called it snake oil and pure hype. This was the AI winter. A period of intense cold, where funding vanished, and the very idea of an intelligent machine was abandoned. The entire dominant strategy for building AI had failed. It had run into a wall. And yet, in that exact same year, 1986, a tiny, almost toy program was created by two researchers in a small university lab. It was not a billion-dollar project. It was a simple experiment. But this single program would prove that the entire AI industry, all the experts, and all the Goliaths of the field, was strategically wrong. It was a demonstration so powerful, so undeniable, that it single-handedly ended the AI winter. It lit a fuse that runs in a direct, unbroken line to the large language models you are hearing about today. This is the untold story of the 1986 program that saved artificial intelligence. To understand what happened in 1986, you first have to understand the two warring factions that were fighting for the soul of AI. This was a strategic battle between two completely different ideas of what intelligence is. In one corner, you had the Goliaths. This was the establishment. The academic superstars, the government-funded labs. This was Symbolic AI. Their strategy was based on logic. They believed that human intelligence was just a very complex system of rules. Their goal was to program intelligence, one rule at a time. Their creations were called expert systems. If you wanted to build an AI doctor, you would interview the world's best doctors and write down every single rule they used. If the patient has a fever and has a cough, then prescribe test X. If test X is positive, and the patient is over 50, then consider diagnosis Y. They were trying to build an artificial mind by hand-coding millions of if-then statements. It was logical, top-down, and meticulously designed. And in the 1970s and early 80s, it was the only game in town. In the other corner, you had the Davids. They were the rebels. The outcasts. A tiny, underfunded, and often mocked group of researchers called the Connectionists. Their strategy was the opposite of the Goliaths. They argued that intelligence was not about logic and rules. It was about biology. They didn't want to program a mind. They wanted to mimic the brain. Their creations were called neural networks. They were simple, simulated networks of neurons that could be trained, not programmed. They believed that intelligence wasn't designed from the top down. It emerged from the bottom up, through learning. For decades, the Goliaths, the expert system builders, had all the power, all the money, and all the fame. The Connectionists were seen as a dead end. Their ideas had been tried in the 1960s and had failed spectacularly. By 1986, their strategy was considered a scientific graveyard. This brings us to our central question. How did this tiny, outcast group of Connectionists engineer the single greatest comeback in tech history? How did a dead strategy, using one simple program, completely outmaneuver the entire billion-dollar expert system industry, and prove that their path was the only true future of AI? That's the question we're answering today. To understand this strategic gambit, we have to go back to the first AI winter. This is the insider secret that set the stage for 1986. The Goliaths had not just beaten the Davids. They had tried to bury them. In the late 1950s, a researcher named Frank Rosenblatt invented a machine called the Perceptron. It was the first practical neural network. It was a simple machine, but it could do something that seemed like magic. It could learn. You could show it a shape, and it could learn to recognize it. The press loved it. The New York Times wrote that the Perceptron was the embryo of an electronic computer that will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. The hype was massive. The U.S. Navy funded it, believing it would be the key to machine intelligence. This terrified the Goliaths. The kings of Symbolic AI, Marvin Minsky and Seymour Papert at MIT, saw the Perceptron not as a breakthrough, but as a threat. It threatened their funding, their prestige, and their entire logic-first view of the world. So, in 1969, they published a book called Perceptrons. On the surface, it was a rigorous academic critique. But in reality, it was a strategic assassination. Minsky and Papert proved, with mathematical certainty, that Rosenblatt's simple, one-layer perceptron had a fatal flaw. It was called the XOR problem. It is a famously simple problem of logic. Imagine a whiteboard with 4 dots. 2 are blue, and 2 are red, arranged in an X pattern. All you have to do is draw one single straight line to separate the blue dots from the red dots. You can't. Minsky and Papert proved that a single-layer perceptron was just like your eye. It could only draw one straight line. It could solve simple problems, but it was mathematically blind to a simple, fundamental pattern like XOR. Their conclusion was devastating. They didn't just say the perceptron was limited. They implied that all neural networks were a dead end. The effect was immediate and catastrophic. The US government, seeing that the kings of AI had declared neural nets a failure, pulled all funding. Frank Rosenblatt's work was discredited. The entire field of connectionism died. This kicked off the first AI winter. Minsky and Papert's expert system strategy had won. The Davids were banished from the field. And for more than a decade, almost no one dared to even use the phrase neural network. But the Davids didn't fully disappear. They just went underground. A few researchers, most notably Geoffrey Hinton, continued to believe. They knew the Goliaths were wrong. They knew the flaw wasn't in the idea of neural nets. The flaw was in the simple, one-layer design. They had a theory. If you could have multiple layers of neurons, a hidden layer between the input and the output, you could solve the XOR problem. A multilayer network could, in theory, learn any pattern. But there was a problem. A big one. How do you train it? If a multilayer network gets an answer wrong, how do you know which neuron in the hidden layer made the mistake? It was called the credit assignment problem. It was the brick wall that had stopped connectionism for over a decade. And in 1986, in a paper published by David Rumelhart, Geoffrey Hinton, and Ronald Williams, they finally found the solution. It was an algorithm called backpropagation. The name sounds complex, but the idea is pure strategic genius. Imagine the network is a factory, and it produces a bad product. The backpropagation algorithm is the factory manager. He starts at the end of the assembly line, with the bad product. He walks backward through the factory. At each workstation, he looks at the worker, the neuron, and, using calculus, assigns them a tiny, precise amount of blame. You get 2 of the blame for this mistake. Adjust your work. You get 0.8 of the blame. Adjust. By going backward through the entire network, the algorithm could assign a tiny bit of blame to every single neuron in the network. Each neuron would then make a tiny adjustment. Run this process 1,000,000 times, and the network learns. This was the secret weapon. This was the engine that neural networks had been missing. It was the key that unlocked multilayer networks and, in doing so, solved the fatal flaw that Minsky and Papert had used to kill the field. The Davids finally had their comeback strategy. But a technical paper isn't enough. They needed to prove it. They needed a demonstration. A killer app that would show the world, in a way no one could deny, that their strategy was superior. Enter Terrence Sejnowski. He was a young researcher at Johns Hopkins University who had just read the 1986 Backpropagation paper. He was obsessed with the brain. And he wanted to find the perfect problem to test this new algorithm. He teamed up with a graduate student, Charles Rosenberg. And they chose a problem that was notoriously difficult for the Goliaths of Symbolic AI, teaching a computer to read English text aloud. This was a nightmare for the expert system strategy. Why? Because English is a chaotic, rule-breaking mess. The letter C is pronounced differently in cat and cell. The letters GH are different in tough and through. To teach a computer to read using the Goliath strategy, you would have to hand-code thousands of rules, and then tens of thousands of exceptions to those rules. It was a brittle, expensive, and ultimately futile task. Sejnowski and Rosenberg's approach was pure connectionist strategy. They built a simple, three-layer neural network. They called it NETtalk. The setup was simple: our input, a string of 7 letters from a page of text. Our output, a single phoneme, a sound, corresponding to the middle letter of that 7-letter window. They gave it a 1024-word transcription of a child's speech, and the correct phonemes for each word. And here is the crucial, inside a secret part. They gave it 0 rules of English. No grammar. No if-then statements. They did not teach it what a vowel or a consonant was. The network was a blank slate. It was a pure, strategic bet. Could a dumb network, using the backpropagation engine, discover the rules of English, all by itself, just by learning from its own mistakes? The experiment began. What happened next is the aha moment that changed the world. Sejnowski and Rosenberg hooked the output of NETtalk to a speaker, so they could hear it learning in real time. When they first turned it on, the network's weights were random. The sound that came out was chaos. It was a directionless, meaningless babble. A random hiss of sounds. It was a computer baby, with a brain full of random connections, moving its vocal cords with no idea what it was doing. Then, they started the training. They fed it the text. The network spoke a sound. It was wrong. The backpropagation algorithm kicked in, went backward through the network, and assigned a tiny bit of blame to each of the hidden neurons. They did this again, and again, and again, thousands of times. And the audience at the 1986 Conference on Neural Information Processing Systems listened. At first, it was just babble. Then, after about 10 minutes of training, a change. The babbling started to congeal. The network had stopped making random noises. It was now making distinct, word-like sounds. It had, all by itself, figured out the difference between vowels and consonants. It was forming pseudo-words. They kept the training going. After an hour, the sounds were even clearer. You could hear the pauses between words. It was like a child, just beginning to sound out words it had never seen. Then, they let it train overnight. The next morning, they fed it the text. It was speaking. A bright, red ball on the grass. It was not perfect. It had a strange, childlike, slightly sing-song quality. But it was unmistakably reading. The network had done it. It had, with 0 pre-programmed rules, learned the complex, exception-filled structure of the English language. But then, they did the final test. They gave it a list of words it had never seen before. Words that were not in its training data. It read them. It had generalized. It hadn't just memorized 1024 words. It had discovered the underlying rules. It had built its own internal, distributed model of how English works. And that was the aha moment. This one, simple demo, proved everything the Davids had been saying for 20 years. The entire Goliath strategy, the expert systems, were instantly obsolete. They were building a brittle, million-rule Tower of Babel. NETtalk proved that you didn't have to build intelligence. You just had to build a system that could learn. The Goliaths were wrong. You don't code the rules. You let the network discover the rules. The NETtalk Gambit was a strategic victory of emergence over design. The audience at that conference knew exactly what they were seeing. This was the proof of concept that broke the dam. The AI winter was over. The Davids had won. If you're getting value from this breakdown and just had your own aha moment, do us a small favor, hit the like button and make sure you're subscribed. We spend weeks researching these hidden insider strategies, so you can understand why the world works the way it does. It's the best way to support the channel. The brilliance of the NETtalk strategy is how it completely reframed the entire debate about AI. It proved that human-like complex behavior, like language, could emerge from a simple network of components, if it was given the right learning algorithm. Backpropagation was the engine. NETtalk was the first vehicle it powered. The Goliaths of Symbolic AI, they never recovered. Their expert systems are now a footnote in history. They are the steam engines in the age of the combustion engine. And the Davids. Geoffrey Hinton, one of the authors of that 1986 backpropagation paper, is now known as the godfather of AI. Terrence Sejnowski, the co-creator of NETtalk, is a legendary figure in computational neuroscience. The Connectionist strategy they championed is the strategy. It's the only one. And here is the final, crucial link. The large language models that are changing our world today, they are direct descendants of NETtalk. They are, at their core, the exact same strategy. They are still just neural networks, only now, they don't have a few hundred neurons, they have billions or trillions. And they are still trained using the exact same secret weapon from 1986, backpropagation. Every time you use an AI tool, you are using a machine built on the strategic foundation that was proven in that one, small lab in 1986. NETtalk was the insider secret that started it all. It was the spark. It was the moment the world, and the future, changed. If you learn something new, hit the like button and subscribe for more strategy breakdowns. And let us know in the comments, what company's strategy should we unlock next?